All right, let's jump right in. For the longest time, self-driving cars were built kind of like an assembly line, right? You had one module for seeing, another one for thinking, and a third for actually acting. But all of that is changing, and it's happening fast. We're right in the middle of this massive shift toward a totally new kind of AI brain for these cars, the Vision Language Action Model, or VLA for short. And this isn't just some minor upgrade, it's a complete rethink of how a car sees, understands, and ultimately drives in our world. So, here's what we're going to cover. First, we'll unpack why this shift was so desperately needed in the first place. Then, we're going to take apart a VLA model and see what makes it tick. We'll dive into the big architectural debate that's shaping the whole field, look at how the most advanced models are tackling some really tough problems, and finally, we'll take a little peek into the future and see where all of this is heading. Okay, first things first, why do we have to throw out the old playbook? Well, that traditional approach, it was a fragmented pipeline, a chain of command from perception to planning to action. And as we all know, a chain is only as strong as its weakest link. This right here, this gets to the absolute heart of the issue, long-tail scenarios. We're talking about the super rare, totally unpredictable stuff that happens on the road. A deer suddenly jumping out, a construction zone that pops up overnight. The old modular systems just couldn't cope. They had this critical flaw called cascaded errors. See, if the perception module made just one tiny mistake, that error would cascade down the line, poisoning the planning and action steps with absolutely no way to recover. Game over. And this table just lays it all out perfectly. On the left, you've got the old way, a fragmented, rule-based system. On the right, the new VLA paradigm, unified and knowledge-driven. So instead of trying to hand code a rule for every single possible thing that could ever happen, which is impossible, by the way, a VLA taps into this huge reservoir of world knowledge, a lot like a human driver does. It's not just following a rigid script, it's actually reasoning about the whole scene at once. And that, right there, is the key to handling the unexpected. So we've nailed down the why. Now let's get into the what. What exactly is a VLA? Let's pop the hood and take a look at the core components. The magic word here is unification. A VLA model isn't just a vision system that's been bolted onto a language model. No, it's a single cohesive framework. It's designed from the ground up to perceive the world visually, reason about what it's seeing using language-like concepts, and then, and this is the crucial part, translate that reasoning directly into a physical action, like turning the wheel or hitting the brakes. Okay, so how does it work? It all starts by taking everything the car sees, feels, and is told, camera feeds, its own speed, maybe a voice command, and turning it all into a common digital language. It's a process called tokenization. This unified stream of data then flows into the VLM backbone, which is really the brain of the whole operation, and this is where the magic happens. The model isn't just seeing pixels anymore, it's understanding concepts like that pedestrian might walk into the street. And from that deep understanding, the action head generates a precise, executable driving command. Now, the core idea is unified, sure, but how you actually build one of these things? Well, that's where things get interesting. There's a major architectural debate going on, and it really boils down to two different philosophies on how you should structure the VLA's brain. And this is the perfect way to think about it. If you've ever read Daniel Kahneman's famous book, you'll know about System 1, our fast, gut reaction thinking, and System 2, our slow, deliberate, analytical thinking. Well, believe it or not, that exact same concept is being used to design these AI driving systems. So let's break this down. On one side, you've got the end-to-end approach. This is one single giant model that does everything. Sees, thinks, and acts. It's very elegant, but it can struggle with latency, being fast enough for the real world. On the other side, you have the dual system approach. This one separates the tasks. A big VLM acts as the slow, thoughtful System 2, doing the heavy reasoning. It then gives high-level directions to a much faster specialized System 1 module that handles the immediate, safety-critical actions. It's a more complex setup for sure, but it tries to give you the best of both worlds, deep understanding and lightning-fast reflexes. And this brings us to the cutting edge. See, these debates aren't just happening in academic papers. The best state-of-the-art models are actively trying to solve the really hard problems that come out of these designs. Let's look at three of the biggest ones: efficiency, reasoning, and feasibility. First up, efficiency. These VLAs are huge models. Some of the early ones ran at less than 2 frames per second. That's just not going to cut it when a car is barreling down the highway. The goal here is real-time performance. We're talking decisions made in under 50 milliseconds. That's the bar. And check this out, a really clever solution. Look at these numbers for a model called latent VLA. It uses a technique called knowledge distillation. Just think of it like a Jedi Master training a Padawan. You take a huge, powerful master model and use it to teach a much smaller, nimbler apprentice model how to act just like it. And the results? Decision time plummets from a sluggish 790 milliseconds all the way down to 210. This isn't just a speed boost, it's what makes the difference between a cool science project and a system that can actually react in time to save a life. All right, next big problem, reasoning. You know, a car doesn't need to have a deep existential crisis about the meaning of a white line when it's on an empty highway, right? But it absolutely needs to think carefully when navigating a chaotic four-way intersection. The challenge is building a model that knows when to just react and when to stop and actually think. This is where a model called Auto VLA is so cool. It has this built-in adaptive reasoning. So in simple situations, it just kicks into fast-thinking mode. Boom, here's the trajectory, let's go. But when things get tricky, it switches to slow thinking. It uses a chain of thought process to logically break down the problem step by step before it makes a move. It's literally thinking fast and slow, but all packed inside a single unified model. And would you look at these results? The breakthrough came from a process called reinforcement fine-tuning, or RFT. Basically, after the initial training, they use RFT to reward the model for good driving and, crucially, penalize it for wasting time overthinking simple problems. And look at the impact. Inference latency drops by 2/3, and the success rate in the really hard scenarios jumps by 14%. The model doesn't just get smarter, it gets way more efficient. Now for the third, and you could argue the most critical problem, feasibility. Look, an AI can come up with the most brilliant, eloquent, reasoned plan in the world. But if that plan requires the car to say, turn on a dime at 80 miles an hour, well, it's completely useless if it defies the laws of physics. So the solution from a model called VLAMP is basically to add a physics expert into the loop. It uses something called a bicycle model, which is a simplified but really effective model of how a car actually moves, and it acts as a final filter. This little adapter takes the AI's high-level, brilliant idea and makes absolutely sure the final driving path is something the car can physically do. It grounds the AI's big brain in cold, hard reality. Okay, so we've looked at the past, we've looked at the present. So where is all of this going? What are the big questions and debates that are going to define the next chapter for this technology? This right here, this is the question everyone in the industry is asking right now. In one corner, you've got companies betting the farm on VLAs. In the other corner, you have companies all in on world models, AIs that are amazing at simulating and predicting what's going to happen next. So which one is the right path forward? Well, it turns out this might be the wrong question to ask. The most cutting-edge systems, like Mind VLA from Li Auto, they aren't choosing one or the other. They're using both. Think of it like this. The VLA is the real-time brain making decisions in the here and now. The world model is the imagination, running millions of what-if scenarios to help train the VLA and predict what other cars will do. They're not opponents, they're partners, two sides of the same cognitive coin. And that brings us to our final and maybe the most important point of all. The performance we're seeing on all these benchmarks and in simulations, it's incredible, but it doesn't tell the whole story. There's a hidden gap between how these models perform in a controlled test and how they do in the total chaos of the real world. This quote from researcher Moritz Roos just absolutely nails it. The true test of any of these systems isn't some pre-canned benchmark. It's how it behaves in a zero-shot, open-world setting. In other words, what happens when it sees something for the very first time? Something it was never explicitly trained for. No safety net. This is where the big industry players still have a major edge over what we see in academia. And so we're going to end on this question. We are making unbelievable progress creating AIs that can reason and drive in a simulated world. But the ultimate challenge, the final frontier, is building systems that are robust enough to handle the infinite, beautiful, unpredictable messiness of our very real world. How we bridge that gap, that's not just some academic exercise, it's the final boss of autonomous driving. And it's the problem we're all going to be watching for years to come.